our roadmap in three parts. First, I will introduce the Qwen 3.5 model. It's a 397 billion parameter model to explain the mixture of expert trick that lets a giant model run cheaply. And second, the model serving part, how we actually deploy the model and why splitting the work across different GPUs saves a lot of money. And third, the measurement. I will introduce a tool from NVIDIA called AI that stress tests the system. Uh, so there's one sentence to remember. A model is only useful if you can serve it efficiently and measure it honestly. So let's make sure we're all have some basic knowledge. As you might already know, a large language model is basically a very good next word guesser. You give it some text, like the capital of China is, it chops that into tokens. A token means a word piece. So it runs them through the model and predicts the most likely next token, uh, like Beijing. Then it repeats one token at a time to write a whole answer. So the model's knowledge lives in its parameters. Uh, we can also know it as the numbers it learned during the model training. So the more parameters usually means the model is smarter, but also it runs slower and more expensive because normally every token has to touch every parameter. So here's a key tension. How do we add knowledge without paying more compute on every single token? That question leads us to our first big idea. The answer is mixture of experts or MOE. Here's the intuition. On the left is a traditional dense model. Think of it as one giant brain, where for every token, the entire brain lights up. Maximum knowledge, but maximum cost every single time. On the right is the MOE structure. Instead of one huge brain, we have many small specialists called experts. When a token comes in, a little component called the router acts like a triage nurse in a hospital. It looks at the token and sends it to just the few experts that are relevant. Everyone else stays asleep. There's also one shared expert at the bottom of the model that's always on. We can think of it as a common knowledge everyone needs. So the payoff is you can store a huge amount of knowledge across all the experts, but only pay to run a few of them per token. So we have a big brain but a small bill. That's the whole magic of MOE. Now let's meet a real model that uses this. It's also the model you will use in the computation. The Qwen 3.5, 397 billion, A 17 billion. Oh, it's a very long name. So the name literally tells the whole MOE story. Let's look at the 397 billion. It means there are 397 billion total parameters in the model. That's the full size on disk. And this A 17 billion means only about 17 billion parameters are activated for any given token. So there are only around 4% of the model switches at a time. That 4% is MOE at work. A few more headline specs of the model. It has 60 layers. Hidden dimension is 4096, and it has 512 experts and a context window up to up to 262,000 tokens, and extensible to about a million. It's also a multimodal model. It understands both text, images, and video. So, why do we care about this model? You get the intelligence of a 400 billion class model, but the running cost and speed closer to a 17 billion model. That's what makes serving a giant like this practical at all. So let's put numbers on it. Inside every MOE layer, the Qwen 3.5 has 512 experts on call, like 512 specialists. And for each token, the router activates just 10 of them. They are also called the routed experts, plus one shared expert that's always on. So there are 11 experts out of 512 are actually working at any moment. And each expert is small, so 11 of them is cheap. And we can look at this chart. The 396 billion parameters sit on disk, but only 17 billion are actually computed per token. That gap, 397 down to 17, is exactly why a model this large can run efficiently. So the sparsity or the MOE structure is the trick. So here's the actual model architecture. So don't worry, we'll keep it high level. Your tokens coming on the left get turned into vectors by the embedding, then flow through a repeating block that's stacked 15 times for 60 layers in total. And each block mixes two kinds of layers. 3/4 use something called gated delta net. It's a linear attention. It's a linear attention that's cheap even for long documents. The other quarter use regular attention. But with a clever setup, 32 query heads, but only 2 key value heads, which keeps the KV cache small. Keep that phrase small KV cache in mind. It will matter in part 2. And critically, after every one of these layers sits an MOE block shown on the right, the router picks 10 out of 512 experts plus the shared expert. So MOE isn't a side feature, it's a woven through the entire framework, entire network. So finally, the LM head turns the result into the next token. And to sum up, the Qwen model, it has MOE and long context support, and that small KV cache make Qwen 3.5 efficient by design. But here's the catch. A great model is only half the story. Running a 397 billion parameter model for thousands of users at once is still very hard. To do it well, we need to understand where the GPU time actually goes when we serve a request. And that takes us to our part 2 of today. So every single LLM request has two very different phases. This is the most important slide in part 2. The phase 1 is prefill, also called the context phase. The model reads your whole prompt at once and builds the KV cache. It's the memory of the prompt and produces just the first token. This phase hammers the GPU's math units. We call it compute bound. And the metric we track is TTFT, time to first token. And the phase 2 is decode or generation. Now the model writes the rest of the answer one token at a time, and for every new token, it has to reread the KV cache from memory. Each step is tiny math, but heavy memory traffic. We call it memory bandwidth bound. The metric here is TPOT, time per output token. So the same request, but the two phases have opposite hardware features. And hold on to that, it's the entire reason for what comes next. So traditionally, when we run both phases together on the same pool of GPUs, this is called aggregated serving. And we can look at this timeline. When a big preview job shows up, as shown in these solid colored bars, it hogs the GPU and stores everyone else's token generation. That's the generation stall on the right. Users waiting for tokens suddenly see them arrive in bursts. There are two problems for this setting. So the one problem is interference. The prefill and decode fight over the same GPU, hurting TPOT. And the second problem is it's one size fits all. We are forced to use the same GPU type and the same configuration for two workloads that want opposite things. So the result is if you optimize for the fast first tokens, you often make the per token speed worse and vice versa. So you are stuck in this situation. And scaling just means buying more identical GPUs. There has to be a better way. So there is the disaggregated serving. So the idea is simple but powerful. Disaggregate to split the two phases onto their own separate GPU pools. So one pool does only prefill, tend to be compute heavy for fast first tokens, and another pool does only decode, tuned for high memory bandwidth and smooth token output. When the prefill finishes, we skip the KV cache over a fast link, for example, NLink or RDMA, to the decode pool, which takes over and streams out the rest of the answer. So we can look at the timeline here on the right. The context GPU and the generation GPU now work independently. The first token delay drops and the interference between the two phases is basically gone. So to sum up, we use the right hardware and right configuration for the right job. So let's get into deeper uh, at how does it work. So why does this help so much? There are three reasons. No more interference, so we can hit our first token and per token targets independently. We can scale the prefill and decode fleets separately to match the actual workload, and it shines on long input, moderate output jobs. Think the code assistants, document QA, RAG, and video. And the diagram shows the workflow. A client sends a request to a disaggregated server, which it routes it into a context instance. Then the KV cache moves to a generation instance, which it streams the answer back. So here I show this disaggregated architecture by TensorRT LLM as an example, but also for all the mainstream LLM inference engines such as sklearn and VLM, they also support these features already. And NVIDIA reports this can deliver up to around 15 times the throughput at the same latency. The catch is coordination. Something has to move that KV cache fast and route each request smartly. And frameworks like NVIDIA Dynamo automate exactly that. Now there are an honest reality check because good engineers know the limits of their tools. Disaggregation is not always a win. It pays off only when two things are both true. The one thing is you have a tight latency target. You actually care how fast tokens come out. And the second thing is your inputs are long enough that preview is heavy and worth isolating. Here's a counter example. If your input to output ratio is something like 1 to 4,000, like a tiny prompt but a huge generated answer, then preview is negligible and splitting it out buys you almost nothing. Same if you have no latency constraint at all. So the real question is, should we disaggregate? And uh, so the real question is maybe not should we disaggregate, it's how do we size it, or how many preview nodes versus decode nodes. So sizing is genuinely hard. We use a shorthand XPYD, X preview workers and Y decode workers. On the left, uh, On the left are all the things you get to choose: the parallelism strategy, how do you split the models across GPUs, and the batch sizes, how many of each worker, and even the GPU type per phase. In the middle are the constraints you must respect: your first token target, your per token target, and GPU memory, total GPU budget, network storage, and multiply that out, and you get, as the box on the right says, over 10,000 possible configurations. And tuning this by hand is brutal, and people sometimes tune it badly and wrongly conclude disaggregation doesn't help. So we need a systematic method. Um, Here's a two-step recipe NVIDIA uses. So the step one is to find individual workers that meet the service level agreement, or the SLA. For a single worker, we try different parallelism combinations, different ways of splitting it across GPUs. For each one, we push the batch size as high, and it goes while still meeting our latency target and without running out of memory. And here's a beautiful side effect of disaggregation. Because preview and decode are separate, we can do them separately. Preview workers just need to satisfy the first token target, or the TTFT, and the decode workers just need to satisfy the per token target, TPOT. So we end up with two shortlists: N good preview candidates on the left and M good decode candidates on the right. And nobody in these pools violates the SLA. And step two, to match them up, think of it like a factory, a producer and a consumer. Preview is the producer. It finishes some number of sequences per second and hands off their KV cache. And decode is the consumer. It takes those sequences and completes the generation, also at some rate per second. And for the line to flow smoothly, the producer's rate should roughly match the consumer's rate. If preview is too fast, decode becomes a bottleneck. And if preview is too slow, decode will cease idle. So we pick the ratio X preview to Y decode where their throughputs match, then sweep the GPU numbers to maximize tokens per second per GPU. So the chart on the right here shows a real result on a smaller model, the Qwen 3 32 billion model. So under a 600 millisecond first token limit, the disaggregation delivered about 148% more throughput per GPU than aggregation, and even under a loose limit over 100% more. And tools like NVIDIA Dynamo and AI Configurator can help you automate this whole search. So we've claimed a lot of speedups. How do we actually prove them? You can't improve what you can't measure, and SLAs must be verified, not assumed. So that's where AI Perf comes in. So AI Perf is NVIDIA's open source benchmarking tool for generative AI inference. In plain terms, it's a load generator. It fires realistic traffic at your inference server and reports back how fast it responded. It works with basically any OpenAI compatible server, like the VLM, SGLang, TensorRT-LM, Dynamo, and even Ollama on your laptop. And you install it with a single line, pip install AI perf. It hands you first token latency, per token latency, and end-to-end latency throughput, and optional GPU telemetry, all in a live dashboard and report files. So let's be concrete about what the AI perf workload actually does. AI perf pretends to be many users hitting your server at the same time. Each request it sends has a chosen input length. We can also call the ISL, and a target output length, the OSL. So you can use synthetic data or real data sets like the shared GPT, so the traffic looks realistic. The requests go to your inference server, the model you already run on the GPUs. And for every single response, AIPerf measures the timing, how long until the first token, how fast each token come out, and the total time. Then it aggregates thousands of these into clean statistics. So you are not guessing, you are measuring exactly the shape of workload you care about. So how do we turn up the pressure? There are two dials. The first is concurrency. You tell AirPerf to keep, say, 100 requests in flight at all times. The moment one finishes, another starts. It's a steady, constant load. The second is request rate. Instead of a fixed number in flight, you say send 5 requests per second, arriving randomly, a Poisson pattern. This mimics real bursty user traffic much more closely. So either way, the game is the same. Turn the dial up, watch your latency metrics climb, and find the maximum load where the server still meets your SLA. That number is your real capacity, how many users you can actually serve. And here's how simple it is in practice. Install with pipe, then run one command, AI perf profile. You point it at your model and your server URL and tell it the endpoint is a chat API. Turn on streaming so it measures token by token, and set your load here. Like 100 concurrent requests, 1,000 total with 1,000 input tokens and 500 output tokens each. Every flag on the right maps to something we've already discussed: the load level, the workload shape, and run it, And AI perf gives you back the first token time, per token time, and throughput. That's your evidence. So if you are benchmarking during this computation, this is the command you will use. So let's tie it all together. The three ideas to one pipeline. So first is the model. The MOE model structure, that's a 397 billion parameter model, cost about as much as a 17 billion one. And serving the prefill decode disaggregation lets us hit our latency and throughput targets and size the fleet smartly. And finally, the measurement, the AI perf proves it all under the real load, and put them together, an efficient model, smart serving, and honest benchmarking, and you get a system that's fast, affordable, and ready for whatever you build this week. So basically everything I showed in this slide is public. You can go deeper. The Qwen 3.5 model card is Hugging Face, and NVIDIA has a great glossary page and a technical blog on disaggregated serving. And AIPerf and Dynamo are both open source on GitHub. So that's it from me. Thank you so much for listening. Yeah, that's basically the training I prepared for today. So I'd love to take your questions.
Thank you, Jiawei. The session was remarkably clear and efficiently organized. Since we have covered the core material, let's dedicate the time to question and answers. Anyone have any questions on Qwen LLM? Either it's deployment or optimization, please discuss with Jiawei. You may ask questions now the time. Okay, Jiawei, then I have a question.
Yeah.
Between SGLang, VLLM, and TensorRT-LM or Dynamo, could you compare how they actually differ on Qwen PD disaggregation in practice in the aspect of deployment and optimization? Which would be the best choice?
Actually, I didn't compare them the actual performance, but I would recommend SGLong or VRM. It would be easier to get started with, and like if you use Dynamo, it's also a good choice. But it's more like a serving framework. But SGLang and VLM is more like inference engines, and they may have better optimizations on the model itself. And as for TensorRT-LM, I think it's a little bit I don't know how to say it. I think the users of TensorRT-LM is not as much as the SGLang or VLM, so maybe the two other frameworks are better. Yeah.
Okay, understand. That perfectly answered my question. Thank you very much.
Yeah, no problem.
I have a question.
Please.
Yeah.
Hello. So I was experimenting with some smaller models with benchmarking and finding out these metrics TTFT and TPOD. And I came across a flag. It says load format dummy in SGLang. So I was just wondering, in the actual competition, will the model weights be present across two nodes, or will we use load format dummy? And where exactly this falls?